And this is also one of the example what we have taken. See, it is a transmission gate what we are writing over here. So for this transmission gate, you can see what is the length and what is the difference between the spacing between one VDD to another VDD. We have mentioned it over here. So the total length means for one inverter. So you can see it is basically three inverters we have combined in series. So for this inverter, so you can see the spacing from one means the width for one inverter, it has been 16 lambda what we have shown in the previous case only. So like this we can sandwich one inverter with another inverter depending upon the circuit diagram what you are going to have. Okay, so this is what we studied, and this is a contact cuts what we are going to use. So if you want to have a means routing of the information, means what the information has to be transmitted from one entity to another entity in the VLSI technology, means then you need to have the routing paths. So the routing paths we are going to define, or we are going to make in the VLSI technology with this lambda based design rules. You can see from the contact cuts, so that is the metal, all these are metals. So you can see the distance between one metal to another metal, we have taken it as 4 lambda. Okay, and we have used the contact cuts and we have used the vanes. You can see these are called as a contact cuts and these are called as a vanes. And basically there are two types of contact cuts we will be using in VLSI technology. One we are going to call it as a buried contact, and one more we are going to call it as a metal contact. So these buried contacts we are going to use it in a NMOS transistor, whereas buried metal contact we are going to use it in a PMOS circuits. Okay, so this is one of the simple diagram. What it shows is, so what is the minimum distance between the routing path or the routing track which you are going to implement in order to transfer the information from one circuit entity to another circuit entity within the PCB board. Okay, so this is how you are going to make a use of it. And you can see here they have given you the transistor, that is a NMOS transistor they have given you. So for this NMOS transistor they have given you two contact cuts. One is for the source and drain. Okay, means it has been connected to some other part. So the distance between the polysilicon to the contact cut means the width of this contact cut is nothing but 4 lambda, whereas the polysilicon area between two contact cuts, it has to be minimum of 4 lambda. So that is what they are showing it in this diagram. Okay, so you just understand this. So how the routing track will be initiated in the circuit design implementation through the use of lambda based design rules. Okay, so we will quickly go to the next section. And you can see the spacing between the NMOS and PMOS transistors, it has been given in this diagram. So you can see the N diffusion and P diffusion, whatever we are going to deploy in CMOS fabrication process. You can see a minimum of 12 lambda spacing has to be there between your PMOS transistor and a NMOS transistor, whereas the polysilicon, whatever you're going to deposit, means the demarcation line, whatever you're going to do the demarcation line, so that has to be a minimum of 4 width length, it has to be there. And it has to be differentiated, means from the N diffusion and P diffusion it has to be differentiated. A minimum difference length of 4 lambda has to be there. So you can see in the right part of this, that is a 12 lambda. So it is a distance or the difference length between the N diffusion with the P diffusion. So after apart from that, the remaining everything whatever we have studied, that is a lambda based design rules. So all those rules will be applicable. So this is a one diagram which will depict for you the spacing between your NMOS transistor and a PMOS transistor. Okay. So in this slide, what you can information you are going to get is that the N diffusion and P diffusion, whatever we are going to select, so the width has to be minimum of 2 lambda in order to make the transistor. And also the distance between from one N diffusion to another N diffusion, or it may be from P diffusion to another P diffusion, it has to be a minimum of 3 lambda has to be there, the first thing. And you can see the differentiation in N diffusion and P diffusion. See, in the stick diagram we used to do it in different color, but here in lambda based design rules we are differentiating the N diffusion and P diffusion. with the use of slope lines. So here for N diffusion and P diffusion, both the slopes are positive only, but in N diffusion the lines are very thinner, means large number of lines are there in a given specific area. When you compare to that, N diffusion will have a less number of lines, means the distance between two lines, it will be maximum in N diffusion, whereas in the case of P diffusion it will be minimum. And we will be using, in order to implement, we will be using a NMOS transistor. So in order to create this NMOS transistor, so we will be using a polysilicon. So what is the length of the polysilicon we need to consider, or what is the width of polysilicon we need to consider, that also plays an important role. So you can see the minimum spacing between N diffusion to P diffusion, it has to be 1 lambda you need to consider during the design procedure. And also that sorry, so the distance between your just wait a minute. The distance between one polysilicon to another polysilicon, it has to be a minimum of 2 lambda, it has to be there. And then coming to the right part of the diagram, so you can see the right part of the diagram, what we have here, we use the metals. Okay, so this metal, we have two types of metal we have used. One is the metal 1 and metal 2. So the metal 1 and metal 2 has been differentiated. You can see for metal 1 we have written a vertical lines, whereas the metal 2 we have written a horizontal lines. And you can see the metal 1 is a minimum width is having 3 lambda, and it is having a maximum width 4 lambda. Okay, and we have written star for these. Why? Because so depending upon the fabrications, it may go either 2 lambda or it may go 3 lambda, or we may go to 4 lambda also, depending upon the circuit what we are going to design in the case of fabrication process. Okay, and the distance between metal 2, that is the metal 2 to metal 2, it has to be 4 lambda. Okay, so and one thing we need to remember is, see, lambda based design rules means there will be no theory type of questions. Okay, so means what, you need to mention this diagram and you need to specify what is the minimum length has to be there, what is the maximum length has to be there, what is the contact cut we will be using, how the contact cuts will be using, and what is the distance between two contact cuts. So this is what you are supposed to write. Okay, so generally when I tell you that okay, lambda based design rules means you will be having some theory based design rules we will be having. It is not like that in VLSI technology. So anyway, we when we are going for fabrication, we will be using the mask layout only for the implementation, or for the circuit implementation. So therefore it is necessary for us to know the lambda based design rules, and we will be knowing this lambda based design rule through the mask layout only. Okay, so there is no any apart from these design principles or design diagram, so there is no any theory type questions will be there for this lambda based design rules. Okay, so with the use of these elements, that is a fundamental elements, we go for the manufacturing of your NMOS transistor and a PMOS transistor. So you can see here, so this diagram also we have seen in the last class also. So you can see the minimum size of the transistor. So 3 transistors we have created, that is nothing but NMOS transistor enhancement mode, PMOS transistor enhancement mode, and the NMOS transistor in a depletion mode. So you can see NMOS transistor and the PMOS transistors, how the mask layout is looking like. So we have deposited N diffusion horizontally. On top of that, we have deposited a polysilicon. So the width of N plus material, that is a P plus material, N plus material in NMOS is, that is nothing but a positive slopes and thick lines are there. So the width is 2 lambda and the polysilicon width is 2 lambda. Therefore, we have written here 2 lambda cross 2 lambda. Okay, so this is a NMOS enhancement mode. Next, PMOS enhancement mode. So in PMOS enhancement mode, what we will be having is, instead of P diffusion, we will be having a, instead of N diffusion, we will be having a P diffusion. So you can see N diffusion is like this and P diffusion is like this. So in the previous slide we saw, right, how you are going to make the differentiation between a N diffusion and P diffusion. So that is what the diffusion means, the difference is between NMOS transistor and a PMOS transistor in case of enhancement mode transistor. Okay, whereas the polysilicon will not change either in case of NMOS transistor or in case of PMOS transistor, it will not change. Okay, next, so we will be using a depletion mode transistor, and we know that the stick diagram, when we are writing the stick diagram, we used to write a yellow color implant, right, for a depletion mode transistor. So in order to indicate that yellow color depletion mode transistor, see, we have written one square box. So this square box, what is the length it has to be? It has to be 6 lambda cross 6 lambda. So means what? Width has to be 6 lambda and the vertical length has to be 6 lambda. So that is the implant what you are going to supposed to create. Okay, so next you can see here how we can make the contact cuts, and what is the difference between the polysilicons. So all those things we have indicated in this diagram. So you can see the minimum separation width. So the left part of the diagram, you can see I am rolling the cursor. The separation from contact cuts to transistor. So the separation between contact cuts to transistor, how much it has to be? It has to be a minimum of 2 lambda. And you can see here the channel means the polysilicon deposition, whatever we have considered, right? So we have taken a larger channel. Okay, we have taken a larger channel. It depend upon the resistance. So we will be seeing the sheet resistance. What you mean by sheet resistance, or what you mean by impedance? So depending upon what type of impedance we want, we can change this length of the channel. So here you can see the length of the channel only this much, but you can see the length of the channel is this much. Why? Because we have increased the sheet resistance capacity, or we have increased the length of this polysilicon. So therefore the length has been increased, and you can see the distance between from one polysilicon to one more polysilicon through the depletion mode transistor, it has to be a minimum of 2 lambda has to be there. Means the demarcation line, you can see here the implant what we are taking, that is a depletion mode transistor we have taken. So the difference between one transistor to another transistor, both are NMOS transistors only. One is having a depletion mode transistor and one more is having a enhancement mode transistor, you can see in the diagram. So the distance is 2 minimum lambda has to be there from one transistor to another transistor. And right part of the diagram, you can see over here, see, even though you can increase the diffusion length, but you cannot reduce the length. Means you can see the polysilicon whatever you are depositing on top of the N channel, so it has to extend or it has to prolong for minimum of 2 lambda. After that you can do any etching, or you can reduce the diffusion size of the transistor or the polysilicon, but you cannot reduce the that vertical length after the diffusion, that is after the channel. Minimum 2 lambda has to be there. So that what it says in the lambda based design rules, and also the same rule will be applicable for the N-type diffusion. So you can see after the cross connection of this polysilicon and the N-type diffusion, so we have extend this N-type diffusion how much? A minimum of 2 lambda. Okay. So in order to form the contacts between the polysilicon and the diffusion in NMOS transistor, so we will be using three different means connections. Okay, so that is nothing but from polysilicon to metal, and then metal to polysilicon diffusion we can make, or we are going to do the buried contact between the polysilicon and the diffusion, and or else we will be using one more important contact, that is nothing but called as a butting contact. Okay, so these type of contacts we will be using in order to have a contact between polysilicon and your diffusion in NMOS transistors. So you can see here polysilicon to N-type diffusion means N-type diffusion material. So how we can make the diffusion? So how we can combine those two layers? So we can do with the use of three. Once again, I am telling you three approaches we can make. One is called as a polysilicon to metal, and then metal to diffusion contact we can make. Either other we can do that buried contact between the polysilicon and diffusion, and also there is one more contact we can establish, that we call it as a butting contact. So the butting contact, what you mean by butting contact? It is nothing but polysilicon to your diffusion will be done using metal only. So that we are going to call it as a butting contact. And you can ask me among three different methods, so which one will be used in almost in all the cases, sir, you can ask me. So for that answer is we will be using a buried contact in most of the cases. So among these, that is a polysilicon to metal, and from metal to polysilicon, that is one contact, buried contact and butting contact. So among these we will be using a buried contact in most of the cases. So why? Because of the advantages in the space and reliable contact. Okay, so we will be using this buried contact. So because it uses a minimum length, that is a contact length, it requires a minimum length. Along with that, it is more reliable when you compare to the rest of the contact. Okay, so because of this only, we will be using these are the contacting methods. And I told you we will be using one more contact cut, that is nothing but vias. Okay, so these vias are nothing but a special type of contact cuts. I told you in the last class only. So these wire cuts are nothing but the contact which is made between from one metal to another metal. We call it as a vias. Okay, so you can see we are making the connection from metal 1 to metal 2. So when you are making the contact between metal 1 to metal 2, we are using a connections, and those connections we are going to call it as a vias. Okay, so these are the design rules for the contact cuts based upon lambda based design rules for contacts. In it might be in NMOS transistor or it may be in a CMOS transistor. In the CMOS lambda based design rules, it has been given in this diagram. Okay, so this completes your lambda based design rules for your CMOS technology. Okay, so next we are going to go for one more important topic. Okay, so this is the NMOS CMOS lambda based design rules. So you can see over here, this and all we have already done through it. Okay, and you can see how the minimum well it has been created. Okay, so the spacing between the channel to channel, separation between P to P, what is the minimum length has to be there. Okay, particular rules for P well creation. See, we have in when we talked about that is a P well CMOS fabrication process. So in the N-type diffusion, we have created a P well, right? So in the P well, we have created a PMOS transistor, and in N-type diffusion we have created a NMOS transistor. How we can make a difference between them, and what is the minimum design rules we need to consider, particularly for when you want to create a P-well CMOS process. So all those diagrams they have depicted over here. So you can see, since in a P-well diffusion you will be having a two transistor, both NMOS transistor and a PMOS transistor, you will be having, and they have taken it as a diffused method. So since they have taken it as a diffused method, so they have implanted the implantation method. Okay, so they have incorporated the implantation, and you can see a minimum of 2 lambda we need to give the separation between one diffusion to another diffusion and between the contact cuts. So these are the minimum rules what we need to follow. And you can see the minimum width. So when you want to reduce the size of the polysilicon means, then the minimum width what you need to consider is a 4 lambda minimum width we need to consider. That is the prolongation of the polysilicon you need to consider if you want to reduce the that is a polysilicon area. Okay, and you can see the minimum spacing to the external thin ox. So means what, we will be using this silicon dioxide on every layer when you want to deposit on the fabrication process. So for each layer when you want to deposit an external thin ox layer means, then what is the minimum separation between those two layers, they have listed out over here. So you can see they have given one is here yes, and they have given it is 5 lambda. So yes, it might be 2 lambda minimum for well at same potential, or 6 lambda minimum for the well at a different potential. Okay, so these are the CMOS that is design rules, especially we will be using in the case of fabrication of P-well CMOS process. Okay, so this is all about the lambda based design rules for the CMOS fabrication method. Okay, so now the next one is uh, the basic circuit concepts we need to understand. The basic circuit concepts we need to understand. So what are those basic circuit concepts is nothing but, see, some of the when you design in VLSI circuit, it is necessary for us to know some of the circuit parameters. So for example, the resistance, capacitance, and the delay associated in each CMOS circuit, it is necessary. Okay, and why we, because we will be having an interconnection for the MOS transistor with different wires. So when the signal is propagating through such a various, or it may be when the signal is propagating through the N diffusion, P diffusion, or a polysilicon, or it may be in terms of method. So then you need to understand these parameters, because these parameter directly affects our the current flowing capability or the load driving capability of the MOS transistor. Okay, so therefore the basic circuit parameters which are necessary for you to understand the current driving capability or the current which is flowing on the MOS transistor, you need to understand means, then these are the some of the basic parameter you need to know. So if you know these basic parameters means, then it will be easy for you to do the analysis for current driving capability of the VLSI circuit. So what are the basic circuits you need to know, then that is the question. Okay, so it may be the resistance. So one of the resistance, what we are going to call it as a sheet resistance. So sheet resistance, it is nothing but it is a resistance which is present, or which is a measure of resistance on the MOS layers which are having a uniform thicknesses. Okay, so when you take some slab, we can say that the slab, or when we take a material which is having a uniform thickness, and if you want to measure the resistance of that material, uniform slab means, then that term or that resistance we are going to call it as a sheet resistance in the case of metal MOS transistors. Okay, so that is one of the basic parameter what you are supposed to know. And also one more important parameter what you are supposed to know is the capacitance. Means since basically the movement of charges from one channel to another channel, or from one entity to another entity, it has to go through charges only. So these charges has to be stored, and because of the dielectric what we are going to use between two layers, so there will be capacitance will establishes within each layers. Okay, so how this layering capacitance will affect our performance of the network, we need to understand. So in order to understand the capacitance effects in the MOS transistor, it is necessary for us to know the capacitance which has been created in various layers in the MOS transistor. So that capacitance also we call it as a basic parameters. It is necessary for us to know in order to understand the complete behavior of the MOS transistor. Okay, so we will go one by one. So the first basic component what you are supposed to know is, we are going to call it as a sheet resistance. So you can see generally this is a sheet resistance. It is a common electrical property which is used to characterize the thin films for conducting and a semiconducting material. So this sheet resistance, it is used to measure the electrical property of a thin films or a slabs, a small thickness slabs we can say, of an conducting or a semiconducting material. Okay, so we are going to measure this sheet resistance on a thin square area of the material. We are going to measure this sheet resistance as a reference of square material. Okay, and this sheet resistance, generally this sheet resistance we are going to define with two important parameters. One is called as a resistivity, that is nothing but rho of the material, and also we will be using how much thickness the material is. So based upon these two parameters, we are going to define the sheet resistance as, it is the ratio of resistivity of the material divided by the thickness. Okay, so you can see in the diagram, so we have one rectangular slab is there, that is a conducting material is there, which is having a resistivity of rho, and which has a length and width of thickness, that is the length is nothing but W, and width is nothing but W, and length is nothing but L, it has been indicated, and the thickness of the sheet resistance we have indicated with the T. Okay, so then thickness is T means then the cross sectional area of this sheet resistance will be represented with nothing but A. So the cross section area is nothing but the width into thickness, we can say that the cross sectional area. So we can write A is equal to W into T. Okay, and if I want to measure the resistance between these two material or with this sheet resistance means, then I need to tie up a knot at the end of the two terminal of the sheet resistance, and then I need to measure the resistance of the material. So if I do that, so we know that in order to understand or in order to calculate the resistivity of the material, we will be using the formula that is nothing but R is equal to rho L by A. Okay, R is equal to rho L by A, where R is nothing but the resistance between the two terminal, rho is nothing but the resistivity of the material, and L is nothing but the length of the element, and A is nothing but the cross sectional area of the material. So the same basic equation we are measuring in order to measure the sheet resistance. So the sheet resistance generally we will be representing in terms of R. Yes, okay. Area that is A, as I told you, A is nothing but the T into that is width and thickness. So if we substitute that, so RA is nothing but rho L by A, and if we consider the length and width as same, then it will become a square of a resistor material. It will become. So in that case, what happens is your length and width will cancel it out. Then the resistance will become RAB is nothing but rho by T. Okay, the resistance, that is a square of the resistive material, we are going to call it as a resistance, sheet resistance, that is nothing but RS. So RS is nothing but rho L by T, that is nothing but the area, means the area of the square material is independent of the sheet resistance. Why? Because sheet resistance is nothing but it is a resistance which has been incorporated in the square of a resistive material. Okay, so means we will taking only the square of the material, and for that we will be measuring the resistance. So therefore RS is nothing but ohms per square, or it is also called as a sheet resistance. So therefore RS is nothing but rho by T ohms per square, so which is independent of the cross sectional area. So in some